We're going to do a small rearrangement. Remember, I said two of the names you might see for enzymes that could potentially do rearrangements. We saw isomerase earlier. Mutase is another one. Phosphoglycerate mutase moves the phosphate onto carbon 2 and scoots the alcohol onto carbon 3. And that primes this molecule for a dehydration reaction. So what I'd like you to do here is ask yourself, if I were going to dehydrate this thing, which is the removal of a water molecule from across a bond, where would I find those two things? Where would I find the H and the OH that are on two adjacent atoms? Take a look for them. We'll reveal them in a moment. Okay, this is where they're located. I have an OH here, it's the only OH, and so if I want to dehydrate something, I'm going to have to take an H from an adjacent atom and form a bond in between. Remember, that is kind of our general methodology for most of our chemical reactions. The ones that involve me ripping something off of a molecule, it's always rip this off one atom, rip this off another atom, and link those atoms. If they weren't linked, I make a new bond. If they're already linked, I strengthen the bond. I turn it from single to double or double to triple. Okay? Moving along then with that, we're going to do that on our worksheet. Here is the 2-phosphoglycerate that we have, and we're going to turn this into its product, and we're going to try this ourselves. So give this a go. Pause the video if you need to. And again, let's draw what we get if we rip that water off. What products do we generate? Okay, now that you're back and have given this a go, most of this is going to stay the same. The OH is gone. The H over here is gone. Phosphate is still in place on there. I still have the COO minus. And then what I've got now is a double bond in that spot in between those two. And of course, I've also now generated a water molecule. And because I'm doubling everything, I got two of these, making two of those, and two waters. Okay, done with page 2 of our workshop. And almost done with glycolysis at this point, actually. As we move along here, the enolase is going to catalyze that reaction, which we just did ourselves. And we've got basically one last step, which involves getting rid of that last phosphate. And just as we did before, we're going to hydrolyze it, we're going to put it on ATP. It's going to look a lot like what we did, for that matter, in reaction number, I can't find the number. Where did it go? I think it's 7. I forgot to number a few of these. At any rate, again, same idea. We're going to put a water molecule on, we're going to add the H to this oxygen, the OH to that phosphate, and we're going to cleave this thing right off. And this time around, since it is not a carboxylic acid, that H is going to stick around. And so I'm going to wind up with this as my product. And you can go ahead and put on the top of the 3rd page of your worksheets, again, the H2O as a reactant, along with another ADP in the service of making another ATP. And of course, double each of those so that you have them all set up. Okay? So this results in something that we would call an enol. In other words, alkene alcohol. So one of each. Turns out enols rearrange rather easily, especially if there's an enzyme around that helps, into a ketone. In essence, the double bond moves from here to there because oxygen loves it some electrons, and the hydrogen ends up popping off onto the other side here. It's not a resonance like we saw when we did Lewis structures. It is an isomerization. Again, because I am going to break the bond between this O and this H and move the H onto the carbon. But the result of it is that we generate this substance right here called pyruvate. And notice, because it's an isomerization, it generates no other reactants or products. This is the end goal of glycolysis. And so now that we've done all of that, we can go ahead and add up everything else that we've done up to this point in order to get this reaction all set to go. And so if I go down the line here, what I will see is I have consumed 2 ATPs and made 2 ADPs. However, right here, you might recall, I undid that. So I'm going to cross those out with these. All right, so So reaction 1 and 2 get their ATP and ADP canceled there. So the front of this sheet only has us making a pair of water molecules. Well, I also used a pair of water molecules at this spot when we were cleaving off the phosphates, so we'll go ahead and cross those waters out as well. So I can ignore the entire front page now. It's been canceled out by other stuff. Not terribly surprising, given that we went activation followed by payoff. Turns out the beginning of the activation undoes a lot of it. So what then have we generated? Well, we've used up 2 inorganic phosphates, used 2 NADs and generated 2 NADH and 2 H pluses. We also generated 2 more H pluses here and 2 more waters there. And then on this spot right here, where are we? At the top of this page, we generated 2 more waters, so that will cancel out with these. And also turned 2 ADP into 2 ATP. So if we add all of this up, what we have at the end of this is 2 NAD plus 2 ADP and 2 inorganic phosphates. And then on the other side, we have the 2 NADHs. We actually have 4 H plus because we've got the ones that came along as part of this reduction, as well as the 2 that popped off because we made an acid. And then lastly, 2 ATPs. So at this juncture, this is what we've got. And so notice we've made a little ATP. We've got a couple of high energy species right there, but this hasn't really generated all that much energy. In fact, the best we can really do if we're in anaerobic conditions, in other words, without a lot of oxygen, from this point is we can wring a couple more ATP out of pyruvate by turning it to lactic acid. That's a process known as fermentation. Doesn't require O2, but if we really want to oxidize this thing properly, we're going to need some help from oxygen to make that happen. And oxygen isn't going to get involved until the very end, but we are going to start the oxidation process in what's called the citric acid cycle in our next video. See you there.